Life Cycle of a Star, Part 2, Black Holes. Review from our last lecture. A black hole is neither black nor a hole. Specifically, it's a larger, denser successor to the neutron star, a collapsed core of a giant dead star or an even gianter dead galaxy. Like any other star, live, dead, or anywhere in the middle, it has a visible accretion disk of orbiting matter. Solar systems orbit stars, galaxies orbit galactic centers, and anything even remotely in the neighborhood of a black hole will orbit the black hole because of its enormous mass. You can't see the black hole, as we'll talk about later, but you can certainly see the accretion disk, certainly in this artist's conception. Now, if this whole set of galactic matter is orbiting around what looks like a giant patch of nothing, I'd say that there's something in that giant patch of nothing, even though we can't see it, and that something must have a very large mass. Just like a star being born in any other very explosive astrochemical reaction, matter gets ejected. X-rays, gamma rays, dust, space schmutz, everything that's heavy enough to have any inertia is going to be blown outward, and it's going to be blown outward in the characteristic conserve your momentum pattern of these bipolar jets. Black holes are no exception. They have bipolar jets like anything else, and if something inside this area where we can't see is emanating more gamma rays than a nuclear power plant, that's again clear evidence for the fact that it's not nothing. The Schwarzchild radius is measured, as usual, from the center of mass of the X star, the black hole. If you get this close to the center of mass, light will go into orbit and not be able to be seen. Let's take a look at some. The event horizon is the Schwarzchild radius is the distance from the center of the star, or the black hole, out to where you are, at the point where the light can't escape and goes into orbit. From this point and onward, nothing can be seen because the light doesn't reach your eyes. Where does that happen? Here, 2gm over c squared. Let's get a sense of scale here. We've got negative 11 powers of 10 here, and 8 times 2 is 16. So we got another 16 in the bottom. That means to have a Schwarzchild radius of 1 meter, we're going to need to have minimum, something on the order of 10 to the 27th powers of kilograms in order to start to get black hole-like behavior. Our Earth is 10 to the 24th kilograms. That means we're going to have a Schwarzchild radius in millimeters. So if you get a few millimeters from the center of mass of the Earth, you may see light going into orbit. Then again, you may not, because the Earth's core is made of molten lava, and nothing can get in there without being vaporized. Problem solved. Similarly for our Sun, which has a mass of 10 to the 30th kilograms, that means we are going to have a Schwarzchild radius in the hundreds of meters. You don't have a Schwarzchild radius if you're inside the Sun. That's why black holes are often tracked in terms of density rather than just mass. How big is a black hole? Well, it's going to need to have enough mass here to work off those 27 powers of 10 in the denominator at a point where you're still outside the material and not vaporizing its core. A small black hole is going to be between 5 and 20 times the size of our Sun, which is already a respectable 10 to the 30th kilograms. A supermassive dead black hole, a dead galaxy rather than a dead star, is going to be 10 to the 5th to 10 to the 20th times the size of our Sun. So minimum 10,000 times the size of our Sun. This will get us out of a lot of questions, such as when will our Sun become a black hole, and what will happen to us if it does? Will we get sucked in like a giant black crater? The answer is it won't. It's too small, and no. Can the Earth ever become a black hole? Certainly not. It's far, far too small, and this is why. Thank you very much, computer and gargantua. We now see what it looks like around a black hole, and we know why we're never going to have one in our solar system. Can we see anything from out here? Yes. And looks like this. This is a telescopic photo of far, far, far out into space with a black hole between here and there. This is not Photoshop. This is what the data actually looks like when it comes in. It's like looking into a spiral camera. It's like looking into a vortex or a tornado or a funnel. It's like the mass has warped space. This is totally in accordance with what Einstein said in 1919 in the laws of general relativity. Huge masses warp space and distort time. If this ball is rolling along a warped mattress, it's not going to run straight. It's going to run around that well there. That's what we call an orbit, and that's why it happens. If the ball is not going fast enough to maintain the orbit, then it will gradually sink to lower and lower levels, just like the coin funnel we saw in class, until it crashes on the surface. Whose fault is it? It's the satellite's fault for going so slowly, going too close, and not being able to move fast enough. If you can't maintain orbit speed, then keep at a safe distance where you can. This doesn't happen because the planet is a giant vacuum cleaner that sucks in everything for miles around. It happens because of basic orbital dynamics, and black holes work the same way. Anything, matter, light, you name it, anything that passes through the space in the vicinity of a black hole will orbit it, assuming it can maintain that orbit speed at that safe distance. If it gets too close, it will find that it can't maintain the necessary orbit speed. It will sink to lower levels and crash onto or into the interior of the dead star. We can see the path of the light rays that got a little bit too close and discovered the hard way that even the speed of light was not quite enough to maintain that orbit.
So, how close is too close? Let's take a look and use our basic equation for escape speed to guide our thinking. If even light can't escape, then we're looking for a situation where we're solving for r, where v escape is the speed of light. Pause the video, pick up your pencil, and solve for r, the Schwarzchild radius, aka the point at which even light cannot escape. Press play when you're ready to check your work. The edge of a black hole, the Schwarzchild radius, will be at a location distant from the star's core of 2gm over c squared. That's where the light is going to disappear. Now, let's check some basic questions of scale. There's g, negative 11 powers of 10. That's 11 powers of 10 in the denominator we have to work off, in addition to the 16 powers of 10 that are already there. That means to have an event horizon of 1 meter in radius, 2 meters in diameter. Mass m would have to start at 10 to the 27th kilograms. Earth, by comparison, is only 10 to the 24th. So we're talking something 1,000 times bigger than the Earth, but less than 2 meters in diameter. How big is a black hole? Well, if 1,000 Earths have to fit on something small enough to sit on the teacher's desk, then black holes have to be millions, billions, extra powers of 10 bigger than our planet. Can the Earth be a black hole? Of course not. Never. Why not? Because if you were 1 millimeter from the Earth's core, that is the Schwarzchild radius you'd get if you plugged in 5.98 times 10 to the 24th kilograms into this equation, you would have bigger problems than a black hole. Specifically, you'd be 1 millimeter away from the center of an enormous ball of roiling hot iron, namely the molten magma at the Earth's core. What about the sun? Can the sun be a black hole? Well, let's plug it in. The sun has a mass on the order of 10 to the 30th. 30 powers up here, 27 powers down there, 1,000 or so. Again, if you are 1,000 meters from the center of the sun, you will vaporize on the instant. Black hole will be somebody else's problem. Can you see from far away the light that's orbiting enormous mass between us and the star. Even though you can't see the enormous mass, you can only see the star. Can you see the light traveling in the curved path? It's crazy, isn't it? I thought light always traveled in straight lines. Well, it does. Light travels in straight lines through space. But if space itself is curved, then traveling straight isn't traveling straight any more than you can drive straight north on Sheridan Road. Drive straight north on Sheridan Road, you're going to end up in somebody's front window in Highland Park. Sheridan Road isn't straight. This is Einstein's model of general relativity, that the presence of mass warps space and distorts time. Picture a ball rolling along the green surface. You can't roll a straight ball across a surface that's not straight. Now, Fc equals mv squared over r, and k equals 1/2 mv squared. The ball is moving much too fast to crash into the planet. It can't get to an r that near. It's got to keep up its kinetic energy. It will go into orbit there and stay into orbit there because it's moving too fast to fall all the way down to the bottom. That's where our orbit comes from. It comes from the warp in the space. If it crashes, well, it crashes because it wasn't going fast enough to sustain orbit speed. It will spiral down and down and down, decreasing that r until it crashes on the surface, with no one to blame but itself for getting too close without checking first that it had enough speed to be able to maintain a stable orbit. Black holes work the same way. Anything that strays too close to a black hole, matter, light, you name it, will drift into orbit as the square root of gm over r, where m is the mass of the giant stellar object and r is the distance from its center. If you get too close, you will go into orbit. If you get way too close, you will spiral down, crashing toward the surface, since you don't have enough velocity to maintain orbit.